Okay, this graph represents a polynomial function of lowest possible degree. The intercepts are integers, which means this really is at 2 and, sorry, negative 2, and this really is at 2. Now, if we're trying to reconstruct this polynomial, everywhere that it crosses the x-axis, we know that we've got at least one factor that's responsible for the x-intercept happening. So this intercept at negative 2 means that we've got an x plus 2 somewhere in our equation. And the fact that we have a crossing point or a root or 0 at 2 means that there's got to be an x minus 2 somewhere in our polynomial. But there's more to it than that. We've seen how multiplicity can affect these things as well. If you have a curve crossing through minus 2, each of these ticks will represent minus 2. There's three ways that crossing can happen. The function can blow through minus 2 like it doesn't even notice it's there. And that we call a root of multiplicity 1. The curve can come down, just barely touch at that point, and then turn back. And that we call a root of multiplicity 2, or 4, or 6, or 8, any even number. And the last thing that can happen is a curve can come along, start curving like it's going to turn away, and then decide, no, I am going to go through. It starts flattening out, but then continues on. It has kind of like an S-bend in the middle of it. And those happen when you have multiplicity 3, or 5, or 7, and so forth. So looking at this x-intercept, this definitely looks like the final case where we have an odd multiplicity. And it could in theory be 3 or 5 or 7 or whatever. They've told us use the lowest possible degree. So when you're doing this kind of intersection, don't worry about the 5 or the 7 or whatever. Use the lowest multiplicity you can get away with. For us, that would be a 3. This right-hand intercept is just a straight crossing through. There's no change in the curvature, so that probably is a root of multiplicity 1. So if we're reconstructing this polynomial, it should look like y equals x plus 2 all cubed, and then x minus 2 to the first power. And in addition to that, there could be some constant out front, and we really have no idea what that is yet. For that, we need some kind of point that isn't one of the x-intercepts. And while they haven't given us a whole lot of well-defined points up here on the arms, where I'm used to seeing it, and while this point is not anything too clear, it's definitely not just minus 3, we do have this. Our curve appears to pass through 0, negative 2. Let's see if that does us any good. That means y is negative 2. We have our constant times 0 plus 2 cubed times 0 minus 2. Minus 2 equals c times 2 cubed is 8 times negative 2. Minus 2 equals minus 16c. So c is 1/8. And our polynomial complete is y equals 1/8 x plus 2 cubed, x minus 2. Looking at this, we have x to the third power times another x means x to the fourth power, so this thing is supposed to be a quartic, and sure enough, quartics are normally shaped like a letter W or with a negative coefficient like a letter M. So just looking very superficially at this shape, this does make sense for something that's x to the fourth power.